Our task for today is to talk about vectors and tensors. We'll definitely go through vectors and get through some of tensors and maybe finish them up by next time. And the way we do it in this class is we're going to do everything in flat space-time as if inertial frames are the only frames in the universe, which is kind of like doing vector calculus in ordinary three-dimensional space as if Cartesian coordinates are only the only coordinates you're ever allowed to use. We can do everything in that setup, and then we're going to move on to general coordinate systems in a curved space-time. And I'll emphasize which things survive from our flat space treatment and which concepts we just have to discard. To get started, let's think about just plane geometry vectors. So yeah, look at those axes. Okay, so if we're doing plane geometry, and in a universe where we're only allowed to do Cartesian coordinates, then we do have this notion of a position vector. So this is sometimes called position vector. And what is the position vector? Well, this is a point, x, y. And this is some position vector, usually denoted something like r with a vector. And we write r equals x hat plus y hat, right? This is all standard stuff for you. Now I'm going to change the notation a little bit just to be consistent with what we're going to do. Instead of x hat and y hat, I'm going to write them as e hat sub parentheses, whoops, that should be y, and e hat sub parentheses x. So just don't worry about the meaning of that notation for now. These are just the things you're used to. These are x hat and y hat, okay? And so the way to view this equation is that e hat x and e hat y, so the e hat, let's call it script I, live in an abstract vector space. So if you remember linear algebra, some axioms. A vector space is a thing with some vectors that you can add together, take linear combinations. There's a zero element. Things are closed under addition and multiplication and so forth, scalar multiplication, okay? So we think of these as just living in some abstract vector space. And of course, x and y are coordinates on the plane. Okay, and this very sort of innocent-looking equation that you learn on like day 0 of like high school physics, I guess. I don't know, maybe day 50 or whatever it is, but it's very basic stuff. This innocent little equation is sort of enacting an isomorphism, a one-to-one correspondence between these two things, coordinates between the plane and the vector space. Let's call it a vector space V. Okay? So the position vector is, formally speaking, a special thing you could do in a flat plane because the coordinates in a flat plane naturally have the structure of a vector space if you're in Cartesian coordinates. Okay? So this construction only works in Cartesian coordinates. If you had polar coordinates r phi, you would certainly never try to write an equation like position vector is r hat plus phi hat. That's not the way it works, right? You may remember from vector calculus and curvilinear coordinates. But we'll get into that later when we do curved space-time. So I just want to emphasize that this is a flat space construction, like this plane. And it will not survive in curved space. So let's see if I can use my fancy method of dragging the screen. No, that's not it. Good. Okay. So now I'm going to do a curve, just a cartoon to see where we're going, of a curved space. And I'm going to think about a sphere. So the surface of a sphere. So S2, surface of sphere. And now we just don't have a position vector. Like, to give an extreme example, suppose I took two antipodal points, like this one and this one on the other side. I'm not going to make it the North and the South Pole, because then you'll get confused with coordinate intuition and so forth. So just two antipodal points on the sphere. Like, what would the position vector from one to the other be? Right? It can't like point through the middle of the sphere. That's not part of the space. Right? We're on the surface of the sphere. So you could imagine trying to get it to like point along the surface of the sphere towards the other point, but like there's a whole family of directions towards the other point if you're antipodal, right? You go, if you imagine you're on the North Pole, you go to the South Pole by any longitude line, right? So like those would all be perfectly good candidates for some notion of position vectors stretching from one point to another. So in general, in a curved space, there's just no notion of a position vector, okay? So no position vector, period. It's just not a thing that's at all useful. You want to talk about 2 points? Fine. There's no isomorphism between points on the manifold, and manifold just being the surface of the sphere, and a vector space. Okay? So I want to kill the position vector right away. This is one of those things you have to unlearn before you learn GR. Everybody happy? Objections? Yes. Please. Why can't I go through the center of the sphere?
Or like if your reference point is the center of the sphere, like why can't you drop a position vector?
The center of the sphere is not in the space. We're on the surface of the sphere. It's a two-dimensional space. Like we're confined to the surface of the Earth, and we're interested in introducing some position vector.
Okay, but you can't pick like one pole, like as a reference?
You could pick the North Pole as a reference, but then what would the position vector to the South Pole be? Suppose I'm at the North Pole, the South Pole is all the way down through the Earth. Now tell me which way to draw my arrow to the South Pole. You'd have to go around the whole Earth, but which direction, right? You can go any direction. So it's just an extreme example of why this breaks down. But in fact, it breaks down whenever there's any curvature at all in the space-time. If it's not exactly globally flat space-time, you don't have this correspondence between position vectors and abstract vectors. Other questions? It's good to object now because, like, I guarantee you, some of you at some point are going to be like doing something wrong. I'm going to say, no, there's no position vector. Yeah.
So, does this mean there would be no longer a notion? Because the position vector, you know, when we talk about it in flat space, it usually has the two components of the direction to some other point, and then however long the distance is.
Right.
I can imagine the distance you can replace with the space-time interval. Is there like still a notion of like direction, or how do you?
Yes.
How do you figure that?
That's a great segue. Absolutely. We need vectors that represent directions, like the vector in this room that represents to Peter, right? That's clearly a good object to be useful to use, even though we are on the surface of the sphere, by the way, right? It's the Earth. So absolutely. So those little local vectors are what are going to survive in curved space-time. And we're going to put a little different vector space at every point in the space-time, and I can draw that. So at some point P, we're going to have our own little tangent space. Okay, and it's going to be VP, tangent space at P. Okay, and it's not a plane that actually extends off the sphere in three-dimensional space. We just draw it that way. It's just there's a vector space at each point in VP, and we're going to introduce vectors, and we're going to talk about how they represent infinitesimal displacements on the manifold. And you've actually already been doing that over here in flat space-time. Right, I do this, drag that way. You've been calling them velocity vectors, right? So the other thing we have is velocity vectors. So the idea with a velocity vector is you take a position vector r, which is some function. Now, usually you think of it as a function of time if it's velocity. We'll keep it as time. And what you do is you take the time derivative, right? I know you didn't pay the big bucks to take graduate general relativity for me to tell you that velocity is the time derivative of position. But there's something very important going on here when we go to curved space-time, or curved space. So this thing is a perfectly good vector because r, the position vector, was a perfectly good vector. That's how you think about it in a flat space, right? But in a curved space, as we'll see, r won't be a good vector, just like it wasn't in a curvilinear coordinate system, but v will be. Okay, so this is the thing that somehow survives. This equation survives. Survives in a curved space. Okay, even though r of t is no longer a vector. Maybe I should say survives in a curved space as dxi dt equals vi. So we don't think of these coordinates. No, these are no longer considered vectors. These are just coordinates, but this is still a good vector. So that's a preview. I'm going to define all of this in curved space later, maybe next week. Okay, but this week we're going to go back to flat space as if Cartesian coordinates are the only coordinates in the world, so that we can always use this isomorphism, and it's just going to be flat space-time, where Lorentz frames are the only frames, only coordinates in the world, so we can use this isomorphism.